Start this recording. Great. Did you have a good break? Everyone's all fuzzy from the break still. I know. Should have seen me this morning. It's not happening. So, let's see here. Okay. So everyone has the chapter 4 notes that we'll be going through. Yeah? Great. Let me turn those off. Lights here. Oh, not those ones. Those ones maybe. Okay. So we'll do a brief review of last day. But of course the video is available, the notes are available, but it was a while ago, so there's a few things I want to touch on before we get going with hypothesis testing today, which we introduced last day, but that was a long time ago, so I don't blame you if you've kind of forgotten. Yeah. So we started talking about, any post-break questions before we get started? Just do it. So, in chapter 4, we introduce inference. Inference is when we take a sample to learn something about the whole population, right? And so there's two main ways that we're going to do that. One being hypothesis testing, which is kind of more formal, kind of established procedure for testing a hypothesis. And the second being confidence intervals. Confidence intervals we'll get to later, but usually people have a hard time with hypothesis testing, so I want to start there, so it's kind of more familiar. And to get there, right, what we said was, okay, we're going to start by talking about, we have one sample, right, and we've collected a mean or calculated a mean from this sample. Right? And so the most basic scenario is that we have one sample mean, right? Kind of basic. But then what we're going to do is we're going to branch out and talk about, okay, well, what if we have a matched pairs scenario? What if we have two sample means we want to compare, right? And then what if we have a proportion that we want to look at? So we'll be looking at all these different scenarios, but they'll all use the same framework. And so that's why chapter 4 is really kind of long and boggy, because there's a lot of rules that we need to establish. The nice part is that once we have these rules in our back pocket, then we can just use those for the rest of the types of questions that we're applying or doing. So last day we said, okay, if an observation, so a single observation follows a normal distribution with a mean, mu, and a standard deviation sigma, that's great. Then it follows that the mean, the sampling distribution of the mean will also follow a normal distribution centered on that same mu, but the standard deviation is going to change to not just sigma, but sigma over root n, so taking into account the sample size. Because it gets confusing to talk about the standard deviation of x bar has the standard deviation in it, right? Instead, we just call this whole lump the standard error. And so it kind of makes sense, right? You take an average from a group, you expect that average to be very similar to the population average, right? And so that's why it's still centered on mu. But because we're expecting these mean observations to be closer together, right? The spread is going to be less than if you're just looking at one observation, right? And it depends on your sample size. So we use that to develop, well, we went through some examples, blah, 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 blah. Actually, blah, 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 blah. You know what I mean. And then we said, okay, well, we can still calculate a z like we have been doing, right? We were doing z as x minus mu over sigma. Now we're talking about x bar instead. X bar is still centered on mu, right? So we can still do x bar minus mu. but then divide it by sigma over root n, right, instead of just sigma. So we're able to calculate this z-score. Z-scores, of course, are the gateway to probabilities, which is where we want to end up, right? We want to find probabilities. And so now that we have a z-score and a way of finding the z-score, we can use the z-table to find probabilities. And we went through and did an example where we did just that. And then we got into the central limit theorem. I'm just kind of plowing through these because we did talk about them last day, but like I said, it was a long time ago. The central limit theorem is as important as it sounds, but also kind of not that strange. Okay. All it says is that as long as you've collected a sample size that's large enough, right, the mean of that sample will follow a normal distribution centered on mu with a standard deviation sigma over root n, regardless of where you took the sample from. Right? So that's kind of cool. So we can take a sample from a skewed distribution and still analyze the mean as if it follows a normal distribution. So that's pretty neat. And I showed you this little graphic just to show you what I meant. We did a big example there. So we took samples from the skewed distribution, and then we plotted the mean as we collected a larger and larger sample, right? As we increase our sample size here, the mean of this group actually gets closer and closer to the population mean where it should be. So, so that's all the central limit theorem is saying. Is basically that we can assume we have a normal distribution as long as we have, usually the main criteria is a large enough sample size, larger than 30-ish, but we're kind of flexible. Okay. That's where we ended off last day. I think, I don't know, I can't remember if we've got into hypothesis testing, did we? I don't have anything written, so. Oh, we did a little bit. Let's pretend we didn't. Well, okay. Maybe let's pretend we did for a little bit longer. Okay. So hypothesis testing, like I said, is one of these main go-to tools that we have. And the reason you all have to take this course is because whenever you want to prove something, you have to do a hypothesis test. Right, so you have some hypothesis, thinking back to, I don't know, elementary school, right? I hypothesize that if I boil water, it turns into gas, right? So we've been setting up these hypotheses. Now it's going to be a little bit different, right? Now we're talking about the mean, but the idea stays the same, right? And so we have some idea, and which we want to test if it's valid or not, right? Significant or not. And so, like I said, the steps that we're going to follow for hypothesis testing, they're going to be the same regardless of what type of question we're covering, right? So if you have a look at your formula sheet, for example, right, everything on the left-hand side going over to the back besides 7.1 and 7.2 is going to be hypothesis testing, right? So until the very end, chapter 7, that's where we get out of hypothesis testing, and we probably won't get to 7.4, to be quite honest, so don't worry. But until chapter 7, all we'll be doing from now on is just hypothesis testing and confidence intervals. And so that's why today, we're going to spend a lot of time just talking about the rules. I'll just kind of blah, blah, blah at you as per usual. And then I'll expect you to have these rules ready for you. Okay. I'm just kind of ready to work with. So first, kind of a quick overview is of these 4 steps. Your first step is going to be to state your null and alternative hypothesis. So just tell me what you think is happening, and what the alternative might be. Okay. The second step is do the test, do the do. Do the test you already know how to do. It's just, we haven't called it doing a test or anything. We just said calculate the z-score. Right? So doing the test is really just calculate the z-score, and then later it'll be a t-score, but we'll talk about that. But calculate a z-score to see how far your sample mean is from your hypothesized mean. So you know how to do that step already. We just haven't done it in this kind of setup. Okay. Step 3 is find the p-value. The troublesome part about hypothesis testing is there's a lot of jargon, right? The p-value, there's the alpha level, all that fun stuff. So it'll take a little bit of work on your part to kind of keep track of what they all are. But find the p-value. The p-value is typically just the area in the tail, right? And so you know how to do that using the z-table, right? So you found your sample mean, and then you have your sample mean is maybe in the lower tail, so then the area in the tail would be everything below it, and vice versa, which you've done as well, right? So steps 2 and 3 we've been doing already, and probably feel way more comfortable doing those than step 1 and step 4, right? But we're just making a sandwich now. So step 4 is draw your conclusion, which is the whole reason we're doing everything, right? Is to be able to answer some hypothesis, some research question. And so it's going to be important, and it's going to cover 3 steps in itself. But in general, you just draw your conclusion. And so that's going to have a couple of steps in it as well, which we'll talk about. Any questions so far? Yeah. So let's see here. I'll just say here, do a little end of review symbol, or whatever you want to call it. And here we're doing February 25th, 2019. So like I said, we have to lay the groundwork and just kind of set up all these rules associated with each of these steps. But once we have them, we'll be good to go. Okay. The tricky part is I can't introduce an example until I've covered all these steps. So a lot of it is going to feel a little bit discombobulated until we do an example at the end. Okay. But we will do an example, and hopefully it'll all kind of click. Okay. So your null and alternative hypothesis are really just statements of what you think might happen and what you're going to assume to be true in the meantime. And so, like I said, we're going to talk about just collecting one sample, calculating the mean from that sample, and then comparing it to some value. Okay? And so one important thing is that your hypothesis has to be about the parameter. So the parameter, remember from like first or maybe second day, but the parameter, shame it got split up, but it's okay. The parameter is a calculation from the population, right? Or a measurement from the population. So a parameter, bless you, has to be something like mu, right? It's going to be a Greek letter. Because we're going to start talking about the mean, right? All our hypotheses will be about mu. Okay? One thing I want you to keep in mind, right, is that's important that we're just talking about the parameter, because if we tried to talk about x bar, right, the sample mean, we know what the sample mean looks like, right? You have your sample, you know everything about it, and so it doesn't make sense to say, oh, I think maybe the sample mean is this. You know what the sample mean is, right? And so that's why we have to talk about the parameter. Yeah. So how you're going to set these up is you're going to have a capital H subscript 0 and a capital H subscript A or 1 if you prefer, but I'm going to stick with A. The H subscript 0, I read it as H naught. Apparently it's H N-A-U-G-H-T. I just would write H naught, but N-O-T. I guess it's not. Or H null, which makes more sense, right? Your null hypothesis. So, and that's what we're doing. We're stating our null and alternative hypothesis. Because these are statements, H naught, HA, we follow them with colons, right? So saying, hey, here's my null hypothesis, blah. Here's my alternative hypothesis, blah. It's not a huge deal. I actually have a typo later on where I use an equal sign. It's okay. I'll change it. I just caught it this morning, but we should be using colons there, right? Just to differentiate. In our first type of question, right, that we're talking about, we're going to be talking about one sample mean, right? Which means we're inferring something about one population mean, mu, right? And so we're going to talk about mu, and in our null hypothesis, just as a fact, we always have an equal sign. Okay? And then our mu naught is going to be a value from the question. Okay? Mu naught is going to be the value that you want to compare your sample mean to. Okay? It's hard because I want to write these down, but I already have. So mu naught will always be the number that we want to compare our sample mean to. Okay? So you found your mean sales to be, I don't know what, 2,000, I don't know, what is it per day? I'm making this up. 2,000 per month, let's say. Let's make it reasonable. So you have your average sales per month is $2,000, right? Is that significantly more than your friend who has average sales of 1,800? Might be worth testing, right? And so something like that. Okay. But so you have your sample mean and a value you want to compare it to, and that's the value that you're going to put here. Notice in your null and alternative hypothesis, whatever you have here has to go here, right? You can't talk about cats and then all of a sudden draw a conclusion about dogs, right? It doesn't work that way. So we have to talk about mu here and mu here, but also the same value that's here has to go here, right? How does mu compare to this value? Is it equal to it or is it not equal to it, right? So once you've decided what this value has to be, what parameter you're talking about, and what this value has to be, then the rest of it is smooth sailing. Okay. The only thing that's different between these two is the sign in the alternative hypothesis. Right. The only difference between H naught and HA, this is probably in the notes somewhere, but whatever. The only difference between H naught and HA is the sign in HA. By default, we're going to use not equal to, right? Our null hypothesis is that the mean is equal to this value, and the alternative is that it's not equal to this value. In reality, right, in the example that I kind of pulled out of thin air, right, if you want to show that your average sales are higher than your friend's average sales, right, then you're specifying a direction of the mean, right? And so now you would want to show that your sales are greater than your friend's sales, right? And so we've got three options for the sign in the alternative hypothesis. less than, greater than, or not equal to. The default is not equal to, right? But usually the question will say, oh, is there evidence that this is less than this, or this is greater than this? And so, I don't know, inequalities used to not be my strong suit. And so I used to do the alligator eats the bigger one. That didn't really help me much. So if you're having a hard time with these inequalities, right, someone just said, well, you just make it an L, and then you can just read it, right? So this is less than whatever it's on this side. So just kind of makes it easier. But if you're good with inequalities, then good for you. Okay. Although I've got a note about it down here, I do want to emphasize it because it's probably one of the biggest questions that I get around final exam time. Okay. So here, for these two, right, less than and greater than, we're only concerned with one extreme. Right? We only want to know if it's less than it. We don't actually, if this is our concern, if it's less than some value, we don't actually care if it turns out that it's greater than that value. Right? Same thing here. If we want to know if it's greater than, right, you don't care if it turns out that it's actually less than. Whereas not equal to, you don't care which direction it's going in. Right? It's just, are they the same or are they not? Right? And so what we do is we call this, the first two, we call them one-sided tests. Remember, we're doing a hypothesis test, so here we're doing one-sided tests. So one-sided or one-tailed tests. And I do have the note on there, but just to emphasize. And then the not equal to is a two-sided or two-tailed test. So I use one-sided and two-sided, but if you prefer to use one-tailed or two-tailed, that's fine by me. So this doesn't actually come up until step 3, where we have to find our p-value. Because remember, the p-value is the area in the tail. And so the one-sided test is just looking for the area in one of the tails, whereas a two-sided test or a two-tailed test is looking for the area in 2 of the tails, right? So this doesn't come into play until step 3. Okay? But like I said, it's probably one of the most common questions that I get, kind of in a panic. How am I supposed to know if I have a one-sided test or a two-sided test? Right? And I'll just say, well, it depends on the sign in the alternative hypothesis. And so what I do when I set up my null and alternative hypothesis, while it's fresh in my mind, I just write beside it if I have a one or a two-sided test. So I'll do that in the example just to try to get you in the habit of doing that. Okay. So by default, is not equal to, but usually the question will specify if you want a less than or a greater than. One thing that we'll note and we'll come back to is that we do all our testing, so all our hypothesis testing, assuming that the null hypothesis is true. So we do all our testing assuming that mu is equal to mu naught. And so that'll come up later, but it's just important to keep that in mind, that we do all this testing assuming that the null hypothesis is true until we have proof otherwise. Any questions? So in step 2, do the test. first test that we're going to do is calculate a z-score. But then what we'll quickly do is we'll move on to t-scores, right? And probably if you've read a research article or whatever, a research paper at any point, they probably did a t-test, right? And so a t-test is this t here. Okay? In real life, real world problems, we'll only ever use a t-score. We start with a z-score, 1, because I have to cover it, and 2, because it's just kind of a nice stable situation, which we'll talk about when we introduce t's, but just to give you a heads up that they're not actually that different. They measure the same thing, right? They measure how far is x bar from the hypothesized mean. Okay. The only difference, if you kind of compare and contrast here, z and t, okay, fine, we know they're going to be different things. X bar, mu naught. The only difference here is that instead of sigma, the population standard deviation, instead we have the sample standard deviation s. So the only difference between z and t is that instead of pretending to know the population standard deviation, instead we're just going to use the sample standard deviation. That's the only difference where they part ways. Okay. And what they measure is the same. How we interpret them is roughly the same. Okay. So I call the z-score your kind of your training wheels. Your t-scores are the real life stuff. Okay. So we're starting with the z-scores, but then we'll quickly move into t's. So like we've said before, right, z tells us essentially how far, how many standard deviations or standard errors now is x bar from mu naught, right? How far is this sample mean from the hypothesized mean? And t does the same thing. So, okay. Great. Software update. Okay, so just as a little note, okay, when we calculate a z or a t, those values, the z and the t, are called the test statistic. Okay. And so if you're ever reading anything, we found the test statistic of, I know, say that 3 times fast, a test statistic, very difficult, at least for me. Of whatever, minus 2.5, right? Then you know that you were 2.5 standard errors below the mean, the hypothesized mean, right? And so that's all it's telling you. Any questions about that? Oh. Okay. Step 3 is find the p-value. So the p-value, we said, was the area in the tail. The formal definition is, the p-value is the probability of observing something, x bar in this case, right, because we're starting with the scenario where we're just talking about one sample mean. So observing a sample mean as extreme or more extreme than what you saw. And the as extreme or more extreme is what makes it the area in the tail. So like I said, in most instances, pretty well all of them, okay, unless there's some sort of weird, wrong hypothesis going on. In most instances, the p-value will be the area in the tail. And this is, so though not completely accurate, this is just me being super, super picky, okay? So it's definitely fine to think of it this way, especially when we're just getting started, but it might be helpful to think of the p-value as the probability that the null hypothesis is true. Okay? So if you think of it that way, if the p-value, so if the probability that the null hypothesis is true is really, really small, right, you're more inclined to reject the null hypothesis in favor of the alternative hypothesis. Right? And that's where we're going to get to in our conclusion, where we use our p-value to draw some conclusions. But I do find this really helpful. If you just think of it this way, right? If the p-value is the probability that the null hypothesis is true, right? That'll kind of help link things up. Hard without an example, but we'll get there. So like I said, the p-value depends on the sign and the alternative hypothesis, right? Specifically whether we have a one or a two-sided test, right? So I've got this little graphic, and this is where I have a typo. I'll even do it in red. How embarrassing. Should be a colon, not an equal sign. Or even like this. I don't know. How embarrassing. Same goes for the others, but I'll only muck up one. Okay. So for example, here's your hypothesized mean. Right, your hypothesized mean is going to be on the center. And then here's going to be your x bar. So what I'm going to do is I'm going to say, okay, here's your mu naught in the center. Here's your x bar. Then this area in the tail is your one-sided p-value, right? The probability of seeing something as extreme or more extreme than what you saw. Notice that this is only true if the alternative hypothesis is that mu is less than mu naught, right? Because then here you've got mu naught, then you want the probability of being less than what you saw. In this other option, if you want to know if mu is greater than mu naught, right? Mu naught is here in the center again, then you want to find the area in the upper tail. If you have a two-sided test, where you have just mu is not equal to mu naught, your sample mean is only going to happen in one of the tails, right? You only get one sample mean. So it's either going to be less than mu naught or greater than mu naught. What you're going to do is you're going to find the area in the tail for one of them and pretend it happened on the other side as well. Right? And so all you do is you find your one-sided p-value and multiply it by 2. Times by 2, pretend it happened in both tails. And then that will be your two-sided p-value. Yeah. So for two-sided tests, our sample mean will only appear in one of the tails, but we will find the one-sided p-value and multiply it by 2 to get the two-sided p-value. I'll add that. To get the two-sided p-value. It's kind of implied, but. So like I said, we already know how to find p-values. That's not the hard part. Hard part is keeping track of what they are and all that fun stuff. But you already know how to find them using the Z table. Right? Once you have a Z score, you can use the Z table to find areas in the tail. Right? Any questions about that one? No? Okay. So, step 4 is our conclusion. Our conclusion, right, is the meat and potatoes of everything that we're doing here. Right? And like I said, it's going to have 3 steps in itself. Okay? but they'll just kind of come naturally because, so what we do is we use our p-value to draw our conclusion. Remember, if we think of the p-value as the probability that the null hypothesis is true, if it's small enough, right, if the p-value is small enough, we have enough evidence to reject H naught, of course, in favor of HA. And so that's going to be the whole goal of this operation. Can you reject H naught in favor of HA, or do you not have enough evidence to reject H naught in favor of HA? And so we find our p-value in step 3. Now in step 4, we're going to use it to draw our conclusions. To determine if the p-value is small enough, we compare it to the alpha level. Alpha is the Greek letter that looks like a fish. It's an alpha level. Okay. And so I know this is where we kind of get bogged down in jargon, right? But the alpha level is just a threshold that says, hey, any p-value smaller than this will be considered small enough to reject the null hypothesis, right? Meaning it's too unlikely for the null hypothesis to be true, so we can reject it. Right? The default alpha level, I've got it down here, it should be closer, but the default alpha level is 0.05. So if you're ever doing any testing and you don't know what alpha level to use, the default is 0.05. And that's kind of industry standard regardless of what field you're in. It depends on a couple of things. You can change the alpha level. If you bring down the alpha level, right? So if you had 0.001 instead, right? Really all you're saying is, I want to make sure that I'm really, really sure about rejecting my null hypothesis. Right? For example, if it's going to cost you millions of dollars to reject the null hypothesis, you want to be really, really, really sure that it's worth it. Right? If we're testing drugs, you usually want to be really, really sure that they work before you bring it to market, right? That kind of stuff. And so the default alpha level is 0.05, but if it's kind of a high stakes thing, you might want to bring it down, 0.01, 0.001 I've seen, right? But just that would be how you regulate it, right? How sure do you want to be in your results? Or really, how picky do you want to be about your results? Or if you don't really care at all and you just want a significant result, then you could bump it up to 0.1, make it nice and big, right? Easy to get an area in the tail bigger than 0.1, right? And so if the p-value is less than the alpha level, we have enough evidence to reject H naught in favor of HA, right? If you're rejecting H naught, you should probably say what you're rejecting it for, right? And so I use the same sentence structure for both of these. I do that a lot, right? I use the same sentence structure and I'll just put a not or leave the not out. But if the p-value is less than the alpha level, your conclusion in terms of the null hypothesis is that we have enough evidence to reject H naught in favor of HA. And so remember, we did all our testing assuming the null hypothesis was true. So then our conclusion has to be in terms of the null hypothesis as well. Whereas here, if the p-value is not less than the alpha level, right? That's the only thing that's changed. We do not have enough evidence to reject H naught. So I'm always talking about H naught. Do I have enough evidence or do I not have enough evidence to reject H naught? So it is less or it's not less. we have enough evidence or we do not have enough evidence. Those are the key layers. And then to kind of wrap it up, once you've decided if you're going to reject the null hypothesis or not, then you can go back to the actual research question and reformulate, okay, well, I've decided I can reject the null hypothesis. What does that mean in terms of my question? Right? And just reformulate the question as an answer. Usually these questions will start, is there evidence that blah, 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 blah. Your sales are higher than your friend's sales, for example. Yes, there is evidence that my sales are higher than my friend's sales. Right? So you always want to answer the question. And kind of a bummer because on tests and stuff, I think people get so caught up in doing all these steps and, oh, I did my huge hypothesis test, that they forget to actually answer the question, right? But that's going to be a part of the conclusion mark. Okay. And here's my favorite. I'm pretty proud of this one. If the P is low, then the null hypothesis must go. Has a nice ring to it, I find. Okay. So one, it's really funny. Two, it's actually really helpful. So it's serving two purposes here, right? Because what we're saying, until we kind of know in our minds, understand how p-values work and how they relate to the null hypothesis, right? Just having Snoop in your mind, what would Snoop do? If the p is low, then the null hypothesis must go, right? If the p-value is small enough, you can reject the null hypothesis. Is sort of what it's saying. Okay? So, and there's so many times where on final exams I've seen written in the corners, if the p is low, then the null hypothesis must go. Got it. All right. So it is a good reminder because, believe it or not, I know how confusing all this stuff is. Right? We've got p-values, we've got alpha levels, we've got null hypotheses, we've got alternative hypotheses, one-sided tests, two-sided tests. It's all this kind of jargon that we will get familiar with, right? But I don't expect you to be familiar with it yet, but I do expect you to kind of work on it. Okay? One thing is that our conclusion, like I said, I break it up into 3 parts. Okay? First thing you're going to do is compare, how does the p-value compare to the alpha level? Basically, is the p-value less than the alpha level, or is it more than the alpha level, right? Or is it not less than the alpha level? Then, what does that mean in terms of the null hypothesis? Do you have enough evidence to reject H0, or do you not have enough evidence to reject H0? And then, what does that mean in terms of the question? Okay. Any questions about that before we do our example? Oh, yeah. We'll talk more about it, but there aren't very good examples or questions available where we pretend to know the population standard deviation sigma, right? And if you just kind of, I'll say it and leave it with you, you can just kind of think on it, right? So what we're saying when we're pretending to know sigma is that we've collected the entire population, calculated the population standard deviation, wrote it down, and then somehow lost all that information, and now we're trying to figure out what the mean might be. Doesn't really make sense, right? But, so that's why we just have this kind of brief, silly example and then we'll get into more real life stuff. Okay? But for now, we're pretending that we know sigma, but that's not always going to be the case, as you've seen by the t-tests. So if we measure the DMS odor thresholds, so DMS odors, I guess, give off odors in wine. You can see how that could be a big deal. I'm assuming it's always present. It's just a matter of, can you keep your odor down, right, as much as possible? And so we all, as individuals, have odor thresholds, right? So there's going to be some concentration where I can't smell it, right? And then at some concentration, I've reached my threshold, and I'm going to start to smell this kind of off odor in this wine, right? So we all have some odor threshold. Right? And what we're saying is that of all individual adults, these odor thresholds follow a normal distribution with a mean of 25 micrograms per liter. Who cares about units? No, I shouldn't say that, but I don't care about units. Okay, so with a mean of 25 and a standard deviation of 7. Okay. So what we're saying is that X, so individual odor thresholds, X, follow a normal distribution with a mean of 25 and a standard deviation of 7. Okay. So I'll just say X, oops, is individual odor thresholds. If possible, my writing got worse over the break. It's possible. Here's our hypothesis. We would like to know if wine tasters, so now we're talking about wine tasters, not just Joe Blow out here, considering all of us Joe Blow, but myself especially. So we'd like to know if wine tasters have a lower odor threshold than the general population. Seems reasonable enough, right? They've got trained noses, trained palates, so they should be picking up on these odors at a lower concentration than we can, right? Seems reasonable, right? So that's what we're going to test. We suspect that they do, but we collect a random sample of odor thresholds for 30 wine tasters. So we've got a sample size of 30, and of course we have to sample wine tasters because that's what our hypothesis is about, so that we can confirm our theory. We find that their mean odor threshold is 21.5. So what we found is the sample mean is 21.5. So here, X bar is 21.5. And of course, N is 30. So we've got our sample mean of 21.5, and just looking at these numbers, right, if we want to know if it's less than 25, well, 21.5 is less than 25, right? I think we can all agree on that. There's no argument there, right? 21.5 is less than 25. What we want to know is if it's significantly less than 25, right? So have we moved far enough into the tail to say that, well, no, maybe the mean isn't 25, maybe it's less than 25. And so here, I just want to make a note. We know 21.5 is less than 25. Okay. But what we want to know, if, oops, we want to know if it is significantly less than 25. But we want to know if it is significantly less than 25. So we've collected a sample, found the mean. We want to compare it to, how does it compare to 25, right? Here, like in most scenarios, we've specified, well, is it less than 25? Right? Because we suspect that their odor threshold might be lower than 25. Right? So for our null hypothesis, I'll just do it over here. I've got kind of a pseudo general format set up there. But when we're writing our null and alternative hypotheses, you can start with just H naught colon, HA colon. That's a good place to start. And then, well, depends on where you want to start. If you're really, really hooped, and because remember, we're going to be talking about all these different types of questions. So on test 2 and on the final exam, right, you'll have to set up your null and alternative hypotheses. So if you're really hooped, a good place to start is saying, okay, well, I know that the null hypothesis has to have an equal sign in it, right? That's always true. So sometimes if I'm really hooped, then that's where I start, and it's going to bubble out from there. I have to talk about a parameter, right? So a parameter is something from the population. And so because I've calculated a sample mean here, the parameter I have to talk about is the population mean. And so that's the value that has to go here in our alternative, or in our null and in our alternative hypothesis, right? So whatever you have here, we have to talk about the same thing here, right? So once you've got that one, you can draw it down here too. Mu. Here, we just have one sample mean that we want to compare to some value, right? And so that value is the value that has to go here. Okay? So we want to know if mu is equal to 25, or maybe if it's less than 25. Just doing a little bit of foreshadowing. So that's what I mean by the value that you want to compare your sample mean to is the one that goes here in your null hypothesis. Okay? I don't want to see your sample mean in there because you know what your sample looks like. Right? You know everything about your sample. So 25 and 25 have to talk about the same thing. The only thing that's different is the sign here. Okay? And what we're trying to show is that mu is probably less than 25, if anything. Right? And so we use mu is less than 25 as our alternative. Here, just to get you in the habit of recognizing when you have a one-sided and when you have a two-sided test, what I'm going to start doing is I'm going to start writing, okay, beside here, I'm going to write in brackets that I have a one-sided test, right? Just to remind myself later on in step 3 when I'm scrambling for, oh, do I have a one-sided or a two-sided test? Right? Because I'm only concerned with one extreme, right? I only care if it's less than 25, right? I have a one-sided test. So I'll just write that here, a one-sided test. So now we have our null and our alternative hypotheses set up. Great. Any questions about that? So far, so good. Hopefully, maybe. Step 2. I've got a lot of gibberish on here, right? But step 2, we're just going to calculate a Z-score, right? And so Z is x bar minus mu over sigma over root n. On your formula sheet, right, we have mu naught there instead in our calculation, but that's because, right, remember we do all our testing assuming the null hypothesis is true, right? The null hypothesis is that mu equals mu naught. And so in our case, we've got x bar of 21.5 minus a hypothesized mean of 25 over sigma, which is 7 over the square root of 30. And I know I've done the calculations here for you, so I'm just going to skip right to it and say that z is approximately negative 2.74. We have to have 2 decimal places. Right? We have to round properly to 2 decimal places for z, because our z table has 2 decimal places. So you have to match the table. That gets a little bit tricky because once we start calculating t's, the t table has 3 decimal places, right? But if you just have a glance at your formula sheet and say, okay, well, I have to use the z table, then you can just see how many decimal places you have to match. Go with that. So, negative 2.74. That's saying that 21.5, an odor threshold of 21.5 is 2.74 standard errors below the hypothesized mean of 25. When we first started talking about z-scores, right, we said anything more than 2 away will be considered extreme, right? So already we're saying, okay, well, that's pretty extreme if the mean is 25. And so already, because this is so large, right, large on the negative end, I suspect that I'm going to be rejecting the null hypothesis. Okay? But we'll leave that for the p-value. But just when you calculate your z-score, you can have a pretty good idea of what you're going to be doing, what your conclusion is going to be. Okay? I've snuck it in here just to show. What if the mean of our sample was 23? So I've got a different color on here, but it doesn't show up that well. Just as a little side note, right, just to emphasize that the z-score can tell us a lot about the conclusion that we're about to draw. Right, so z is x bar minus mu naught over sigma over root n. Let's just pretend for a second, and we're just doing this on the side. It's not going to factor into anything, but we're going to do 23 minus 25 over 7 over the square root of 30. I think I don't have it anywhere, so I'll just do it. 7 divided by 30 square root. So here I get negative 1.564921593. So yeah, 23 is less than 25, but because it's only 1.56 standard errors below the hypothesized mean, it's probably not significantly less than 25. And so there's this idea of there's a realm where things are not significantly different. And so I kind of think of it as, okay, well, here I'm standing at the desk, right? But even if I'm standing here, you would still say, oh, she's over there by the desk, right? It's not until I've moved, somewhere way out here that you would start saying, well, no, she's not over by the desk. She's over here by the whiteboard or something like that, right? So it's the same idea. We've got this realm where, yeah, 23 is less than 25, but it doesn't look like it's significantly less than 25. Right? And so that's what we're going to be doing. Whereas here, with our wine tasters, it looks like their odor threshold is significantly less than 25, just because of our Z-score, right? but we're going to translate that into probabilities using the p-value. Okay. So we just did the side note, right? This little side note. You can forget it now. Our p-value, right, if you draw your, oops, change colors. You can draw your normal distribution just like we have been doing. Your hypothesized mean is going to be the value in the center, so 25. And we found a sample mean of 21.5. And we wanted to know, okay, is the mean less than 25? So that means we want the area in the lower tail. And so this area here is your one-sided p-value. From the Z table, we find that the area to the left of a Z of negative 2.74 is 0.0031. This is going to be our one-sided p-value. I just said p-value, but it should be our one-sided p-value. Sneak that in there. Really tiny. So this will be our one-sided p-value. And so what we're saying here is our one-sided p-value is 0.0031. For our conclusion, we take our p-value and we compare it to our alpha level. The default alpha level that we're going to use is 0.05. 0.0031 is less than 0.05. And so what we're going to say, and we're going to use this sentence structure, since our p-value is 0.0031, it is less than our assumed alpha level of 0.05. That's just me saying, hey, because I didn't give you an alpha level, right? If you're assuming an alpha level, you may as well say it. So it's less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. So this will all be part of answering the conclusion part of your hypothesis test. Compare the p-value to the alpha level, right? That's your first step. What does that mean in terms of, can you reject the null hypothesis or can you not reject the null hypothesis? And then finally, I've got it way down here at the bottom. We answer the question, what does rejecting the null hypothesis mean in terms of the question? That means that we can conclude that wine tasters have a significantly lower odor threshold than the general population, right? Because in rejecting the null hypothesis was that the mean odor threshold for wine tasters is also 25, right? We assumed that until now at the end, we're saying, well, that's not looking to be that true anymore. So now we can reject that null hypothesis and say, no, the mean odor threshold is probably less than 25. Right? And then you can reword your answer or the question as an answer. Okay? So the highlighted sections here would make up a complete answer. And then I've got some kind of mumbling in the middle. Okay. Any questions? No. So that's a lot. I think that's good. We'll start on confidence intervals next day. But yeah, so if you had to go home and memorize anything, I would say it should be these two statements. Right, so it's on the Snoop Dogg page, because this is where your conclusions are going to come from. This is where you kind of show what you're made of. Right? You've done all this testing, now it's time for conclusion. So depending on how the p-value compares to the alpha level, we'll be able to state our conclusion in terms of H naught. So here are the two options, remembering that you're always stating your conclusion in terms of the null hypothesis. Right? So maybe go home, write these on little cue cards or sticky notes and stick them all around your house until you memorize them, and they won't make sense still, but at least you've got them in your head. But that's good for today. I'll see you guys on Wednesday or in the lab, I don't know. Or both.